Writers write what they know. Liars write what they wanna show. Singers sing what they told. But I know you got something else to say. Like secret language, speaking in tongues. Snake like tongue tied, you on the run. Tribal dancing, I don't know what you are, you are, you are, you are. Summer floating over my heart. We're both dancing over the dark side. I don't know who you are, you are, you are, you are. You got letters sprinkled all over your body. If I join up the dots, it makes me feel naughty. I feel like I shouldn't touch. You got a no touching sign. I feel like I shouldn't run. You're blocking the exit with your life. Addicted to light, center, always in the limelight. Show ya a real good time. Oh, I know you got something else for me. Like secret language, speaking in tongues. Snake like tongue tied, you on the run. Tribal dancing, I don't know what you are, you are, you are, you are. Summer floating over my heart. We're both dancing over the dark side. I don't know who you are, you are, you are, you are. You got letters sprinkled all over your body. If I join up the dots, it makes me feel.
Hello everybody, we're back for another day of practicing binary exploitation using the nightmare challenges or nightmare course of CTF challenges. Today's challenge is going to be the Sunshine CTF 2017 challenge called Alternate Solution. I don't know. Just from the name, I'm guessing there's one obvious solution that presumably turns out not to work. And then you need to approach it in a different way. Let me get my third terminal going, because why not? So yeah, I'm going to work on this one. Hopefully I can get it done on this stream. I was also sent another challenge from a viewer of the stream, and if I can get this alternate solution done, then I will try to work on that one as well. So I've already copied in the binary, and I will start with the usual. Let me start in the top terminal. Doesn't really matter, but we'll keep it that way, I guess. Start with the usual. Look at it in file. And it is a ELF binary, 64-bit, dynamically linked, not stripped. That is helpful. It's dynamically linked, so let's check out what it's linked to. Just libc. So if we need to do a ROP thing, maybe we could use one gadget, pull out the gadgets from this libc, which at this point I should probably just have memorized because there's only like 3 of them in the 64-bit libc binary on this system. And let's check the security settings. Probably we've got NX enabled. Full rel. Oh, everything is on. All right. Okay. So we got full rel. Cannot change the global offset table or the procedure linkage table memory. Got stack canaries. Can't overflow without dealing with that. And since this is in the array indexing category, I don't think we're gonna have to worry about canaries, even if we're dealing with stuff on the stack. NX is enabled, so we can't put our code on the stack or really anywhere. We can't write to it and then execute that code. So no shellcode options unless we use ROP to change the memory protection on a segment, but that's probably not what is required here. And then PIE is enabled. I think this is the first binary that we've seen in the entire sequence so far, which is a couple dozen different binaries. I think this is the first one that we've seen with PIE enabled. So because we've got ASLR turned on this machine, we don't even know where the segments for the binary itself are going to be loaded in, let alone where the libc segments are and where the stack and the heap are located. So we have no clue what the addresses are for anything. Maybe it will leak us an address and that will be handy. Maybe whatever we're doing with the array indexing means that we don't need any knowledge of absolute addresses. That seems plausible to me. If we know the relative address for a piece of data that we want to change, the address of that data relative to the start of some array, and we have out of bounds writes for that array, then we can just force it to write relative to the start of the array. And if they're in the same segment, then they're going to still be mapped the same offset from each other, so we could make use of that potentially. Given all of this, I'm just going to run the program first and see what it displays, or in this case doesn't display. Going to give it some input, and it says too low, just like your chances of reaching the bottom. Okay, so it's a little bit rude, but fine. So we'll go ahead and open it up in Radar because I don't know what's in this thing. There's no output. There's no obvious leak. We could, maybe if I say a number, yeah, too high. And I don't think it's like, yeah, so it's trying to treat it as a number, and when it reads in the word test, it's just going to give it 0, because you're doing probably A2I or something. Hey, Furay, thanks for joining, Royce. Yeah, it is. I mean, this is, they're putting a little snark in there, so I'm not a fan of their attitude. All right, so we opened it in Radar, and we put the AAA in there to analyze the binary, and we can run AFL, and it'll find the functions that are in here. We have the main function, which interestingly is sim main. Usually it's just main. I don't think that matters. And then we've got our imported functions. It doesn't look like there are any other functions that are from the application developer rather than from the libc library. And we've got exit, fopen, fget, printf, a2f, puts. So it's actually a2f, not a2i, which is interesting. So we're giving a number that is a floating point value, I guess. Yeah, I don't know. So it's going to interpret that with decimals and stuff, and apparently 53 is still too large. So let us go to the main function, pop it open, and we can start looking at what we have in the assembly code for it. We call fgets on standard in. So this is us reading in apparently 10 characters, and we will read them into a buffer starting at EBP minus 4a, this variable on the stack. And it doesn't overflow to the next thing on the stack because we read in 10 bytes and it's 10 bytes away from the thing below it, or I guess technically above it. Okay, and then we call A2F on that. So yeah, we've converted that to a float, or maybe a double. A2F returns a double. So, okay. Got our double wide floating point value. That'll come out in XMM0, and we do whatever this instruction is. I am not that familiar with the floating point instructions. And these are, I guess these are not even the floating point, like FL whatever instructions from, what do they call it? X87, I think. This is like the SIMD stuff from maybe SSE instructions. So let's go ahead and I'm going to copy that instruction name, and we're going to go throw it into our search for x86 instructions. And this one is convert scalar double precision floating point value to scalar single precision floating point value. So what this is doing is taking the double and turning it into a single, so to speak, float. So from a 64-bit floating point number to a 32-bit floating point number. And I guess it's putting that 32-bit one in the XMM2 register. Okay. And then we store that into memory at 5C. So in this variable here. And that should be fine. And then we convert it. I'm guessing this is the opposite of this one, just from the naming convention. Convert to single, I don't know, scalar single to, yeah. I don't know what the T is for. Maybe CVT is convert. So like convert scalar single to scalar double. So then after converting it from a double to a like single floating point value, we convert it back to a double, which is confusing for me. I don't understand why they would go for that. And then we call move SD. So that's like move scalar double is my guess. Move or merge scalar double precision point. Okay. Which version are we using? I would think this one, because it says like keyword and then this value, but this address is not. Oh, this is, I guess, relative to where this memory segment gets loaded. Maybe that's the thing. So what we could look at is if I run this in GDB and disassemble the main function, then where are we looking? We're looking at this move instruction. So Radar has tried to turn this into an address, but the reality of what that instruction says is that it is the instruction pointer address. So wherever this bit of code happens to exist in memory, offset by 1BE hex. So we could maybe say print out that value in Radar, which is, how do I print a double? There's got to be something, right? We're back to like floating point stuff, and I was not having a good time with that on the, like, I worked on a challenge two prior to this one, Royce, and it took me 4 separate streams. I think it was a total of like 12 or 13 hours, and that one was all about inputting your hacking input stuff as floating point numbers, which then get converted just to like binary. And if you give it the exact right floating point numbers, then it converts to the binary that you need it to be in order for the hack to work. And it just like adds a whole layer of fucking with my head. So I hope that's not what we're going through here. But I do need to figure out what that number is. Maybe I can print it in GDB. Examine one. We say, oh, what is the, I want it as just F for float. Okay, so examine one floating point giant at 0xA70. Okay, so this is the number. If it's above this number, then we'll get the too low. Or, sorry, if it's below this number, wait a second. If our entry is below, yes, sorry, if we're below this number, no. Yeah. So if this number is not below or equal to our number, because the order of this comparison, this is the 37.39359. And if it's not below or equal, then we come down the red case and go to this bit of code, which prints out the too low. So let's double check that, make sure that I actually am interpreting this correctly by just running the program. If I throw that in, it says it's too low. If I throw that in, but we do 9 here instead of an 8. No? Interesting. What if we do just like 3, 6? Then it's too high. So this, ooh, Okay, I see what's going on. Or, I mean, I don't like understand what's going on, but I see why we got the too high notice. So we first give a number, and if that 36 whatever is not below or equal to what we gave, then we'll get the error message. Then we load the exact same number, and if then so we have to give a number that is exactly equal to that, I guess. Something that converts. That is tricky. And then it'll print the flag for us, and we need to actually create the flag txt for that to work. But at the same time, since the name of this thing is alternate solution, I'm assuming there's something else we might be able to do. But what I'm seeing in this challenge is they take a number that has 64 bits of precision. So a lot of decimal places are supported because it's 64 bits of data to represent it. Then they convert it to the 32-bit version, which loses precision. So you basically are chopping off a bunch of the decimal point, like places. And now maybe you've got only 3 or 4. And then they convert it back to the 64-bit and say it has to be exactly equal to this particular 64-bit number with the full precision of that, which I would think is not possible. At least that's like, at first glance, it doesn't seem like you would be able to get around that. So maybe that's what the alternate solution concept is about. At the same time, I don't see how to even get into the rest of this code if we don't pass both of those checks. So maybe we do need to figure out a way to pass that check, and then something else happens here. But this is like, we open the flag file, we get the string for it, and then we print that string. And then why do we loop back? It's kind of a weird case. I guess we are just looping and printing stuff until there's nothing else to print from the flag file. So in case the flag is really long, it won't fail to print the whole thing. It'll just print a little bit and then loop back around and print another little bit. Okay. And then we basically leave the program. So why would this be in the array indexing section? That is a conundrum for sure. Why? I mean, what we can attempt to do is just straight up figure out a way to get that number, but it's not going to be. You can double check, but I think the D in this indicates it's like doing a double precision comparison. Unordered compare of scalar double precision floating point values. So yeah, we are comparing the two things as double precision 64-bit floating point numbers. Whew. So that's why we were getting too low when we just pasted this in, because it got converted down to a float, which probably might have lost us this chunk or something, and 5-0 is going to be lower than 5-5. Something like that. Or maybe this, yeah, because if it, I don't know where it lost the precision, but ooh, that's tough. And again, it feels like there needs to be an alternate solution. I can put in nan, but okay, that seg faulted, which is real interesting. Sorry, flag test, just in case that was seg faulting because we didn't have the flag.txt. I don't think so. No, that was it. Okay, wow. This challenge does have an alternative, but it's a lot simpler than I anticipated. So this is something that I thought of because in dealing with the previous challenge where we were inputting doubles, I was trying to generate some doubles that had a very specific bit pattern that turns out not to be, when you use that pattern of bits for the actual underlying data, the binary data for the double, when you say interpret this as a floating point number, it goes, that's not a real number. So that gets used as a value called NaN for not a number. And when you say then print it, it just prints NaN. Well, the reverse also works. It will read NaN as a valid input to convert to a float. That makes sense. So, like, I think I can, how do I say float? Can I do it like this? Yeah, so I can probably do this. Right, so float will also take nan when you want to convert from a string, which is what we have provided on the input here. We provided a string of 3 characters, and it'll do like negative infinity and positive infinity. There's a few special values that are allowed in the floating point, the IEEE 754 standard for floating point. So you've got negative infinity, positive infinity, and nan. So in this case, nan is a kind of value that always compares. I would have thought that nan would go down the red case for both of these, just because I think it doesn't sort in any particular relation to any other floating point number. It is neither above nor below nor equal to any other number, just because it isn't a number. So it's weird to me that the below or equal test worked, but probably somewhere in here there's rules about why nan gets treated that way. The unordered result is returned if either source operand is nan. So what is the unordered? And apparently there's a QNAN and an SNAN. Maybe QNAN is the like double precision version and the SNAN is the single precision version. I see. So there are 3 possible outcomes, or 4 possible outcomes from this comparison. It could be greater than, one number could be greater than the other, it could be less than the other, both numbers could be equal, or they could be considered unordered, which is what happens when you get nan. And I guess the particulars of which flags get set when you have an unordered outcome from that comparison, when we do the comparison, then the next instruction, the JBE, is reading certain flags to determine how to behave based on how those flags were set by the comparison. And I guess it turns out that the unordered result sets flags such that the JBE works. And since it's unordered in both of the comparisons, both of these will pass. So, okay, that was pretty good. We can read through the walkthrough, but it's going to be real short because, oh, and they say right at the top. I mean, I don't try to read the readmes before going into it because I don't want to spoil anything for myself. I want to have as much of the challenge as possible. Coming at it fresh like it was a CTF challenge that I am playing live or something. But they say right away, a bit of a spoiler, this isn't exactly index related. However, at the time, this is the best place I thought to put this. I mean, that might be true when this was added, but now they have a whole section for grab bag where I just feel like just throw weird stuff in here and don't, this is in the category of weird. Yeah. So there you go. You put in Nan, and then that's the flag that I guess was there during the real CTF. Yeah, they say the same stuff that I talked about. Okay, cool. So let's see if we can do the next one, and that'll maybe be a more serious challenge. And then if this works, we'll go on to the, I think it was called Rop Me challenge that was sent in by Julian. So let's get going on the next one and see if we can do both of these in one stream. And then I'll be done with the array indexing section, which I think all told isn't such a bad thing, except for that first one was just the most difficult experience I've had so far streaming these challenges. Okay, get to that directory, copy in the binary, and get out of radar. All right, same deal. We are going to look at it in file. This one is called Dream Heaps. Hopefully this one is still an array indexing challenge. So the last one wasn't really an array indexing challenge, which is what worries me, that like maybe this one also is not. And the fact that it's called Dream Heaps might be a hint that it's a heap-based exploit challenge. And I have not done any of those, and I haven't really learned about how to do those yet. So if it turns out that's maybe what we need to do, I might set this one aside, come back to it when we get to the heap section, and I'll go off and do some like more instructional stuff to learn about how to exploit heap vulnerabilities. But let's approach it with the assumption that there is an array indexing approach to solving it, because I think I understand how to take advantage of those vulnerabilities. So it's 64-bit elf, dynamically linked, not stripped. Okay. Not dot slash. Linked to libc. Okay. And then check security. It's got partial rel row. Canaries are on, NX is enabled, and no PIE. Okay, so we've seen this sort of level of protections before. We can take advantage of this. We can make a ROP chain, perhaps, or just with partial rel row, maybe the array indexing will let us overwrite something in the global offset table and get a function to call a different function than it should. That's always fun. I say always, but I haven't actually done that with array indexing, but in theory. Online dream catcher. Write dreams down and come back to them later. What would you like to do? Write a dream, read a dream, edit a dream, or delete a dream, or quit? Okay, so this kind of menu setup I've seen in a few CTF challenges where you're probably creating a data structure in memory using these commands. So if you write a dream, it like adds a new entry to the data structure list or array, however it needs to store it. And then read is just like access one of those existing entries. 3, edit a dream is maybe now write a different value to an existing one. And with this being array indexing, it's entirely possible that the exploit to solve it is basically, let's say if we say read dream, even though we haven't added anything into the data structure, if we provide an index, we could provide a negative index, or we could provide a very large index, something larger than the number of entries we've added, then maybe it will simply read the memory at that offset from where the data structure starts and allow us to simply read any kind of memory from anywhere in the program's memory space. So I'm going to start with that and just maybe do a -1. And so it says null. That's interesting. About -2. Okay. -1000. We got a seg fault. So maybe it tried to access memory that it shouldn't have. We can look at that. So we try to access memory at this address. Now if we do -1001, get a same seg fault, and we can see we try to access memory at this address, which is 8 bytes off, because this is going to be hexadecimal. So instead of at 600,160 hex, it's at 600,158. So we went down one chunk. So this is reading an 8 byte, or the indexing is by 8 byte elements, basically. So we could probably we could probably write a script that would run this a bunch of times and read out the memory for whatever's in the program. But I don't think, that feels like it's not the most effective way to start working with this. I think I'm going to open it up in Radar, look around at stuff, see if there's anything that looks enticing to either write to or read from. I would imagine the GOT is the way to go on that, but we'll have to see. With no PIE, the addresses that we have from the Dream Heaps program are known to us even without a leak, although this is like a tool for leaking data, so we might have been able to leak a useful address anyways. But probably, since it's called heap, maybe the dream info is allocated on the heap rather than the stack, so I don't know that we could leak a stack address, but we could leak a heap address perhaps. At the same time, the heap and the stack should be randomly allocated because we have ASLR turned on, but these are not random. 2 different runs of the program have it at the same location. So I'm going to say wherever this data structure starts in memory, which we could easily calculate, 160 plus 1000 times 8. So the memory, the data structure is located in memory at 602.0A0. And I'm sure that we will be able to confirm that when we look at it in Radar. So open up Radar, analyze it with AAA, and then seek to the main function and open up the visual graph mode. We turn off buffering. We print out the online Dreamcatcher sort of header texts. We print out the menu. And where are we jumping to? Okay. So Radar hasn't figured this out for some reason. But we basically have a jump table located at this address. Whatever our selection is for... Yeah, why hasn't Radar like been able to show... Can it show me it in... What is it? PDF? Nope, it thinks that's the end of the function, which is interesting. So this is going to jump to some address based on the index that we gave for the menu selection. It's basically the kind of code that you get if you wrote a switch statement. In each case will be put at a certain... We'll make a little table in memory, and the address of the code for each case is put in successive entries in that table, and then we just index into the table based on the number. So if you select 1, then I don't know if they call it decrement or anything. I guess not. So at location 1 within the table, so the offset 1 from the beginning, will be the address of whatever code we need to jump to. And unfortunately, Radar is not showing us that table and hasn't linked it in to show us the code where it could go to, which is too bad. But that's, I think we can deal with that. We can look at this stuff in GDB for sure. And there is, actually GDB sees more of this function. So all of this code is what comes after the jump here. And so this is presumably where we jump to for the first menu option. And then it'll jump back to the beginning of the menu stuff, I think. B74, which is here. So they all jump to the end here, basically. And then jump back to... where... I think jump to this puts? That's surprising. Real quick, I want to see what is printed with the puts. Not an option. So this is the case for, this is sort of the default case. If you provide a number that is not 1 through 5, then it'll jump to here and say not an option. It'll print that out, and then they all go into this jump at the end, which just says jump all the way back up to the beginning of the menu. So, okay, that's how you get the repeating cycle. This is the loop that we have. So if we look at read dream, we can look at that in Radar, actually. It's gonna be sim.readdream. And which dream would you like to read? You do puts of that. We scan in a number. It puts that into I see. So What is it? Print hex. PX. So, what have I done here? Go back to that function. Okay. Can we go back to that function? Cool. So if we say PX 4 at obj.index, then we have well, that's neat. That's surprising, let's say. So the code that we have scans in a number that we provide. In my case, I was doing like -1000 in some of these. And then it loads a fixed number that's just like statically put into the program and checks it again. Or this is probably not statically put in the program. This is okay. So this is put into it's a fixed location in memory to store the number, and I imagine the number that gets stored is actually how many entries we have added to the dream database, let's call it. And so if you provide a number that is larger than why would it be that way? So we load index into EAX, and then EDX is going to have the number that we just scanned in. When we compare EDX, EAX, oh, wow, I was looking at JLE and being like, jump larger equal, but it's jump less equal. So yes, that's what I thought. If we provide a number that is larger than the index number, whatever that happens to be based on how many entries we've added, we will come down to this case, which doesn't actually read the memory. So we can see that if we run the program and I just say read and I put in 5, it says, you skipped a few nights, and then it doesn't actually print out what I wanted to enter. Now if we say 2 and put in 0, that is equal. So we should get the success case. It'll probably print out something. Maybe it'll be null. Yeah, so then that is null. Okay, but we can always do a negative index because negative value is always going to be less than 0 or more. Or, index is going to be 0 or higher. And so we can always provide a negative index and have this check succeed. Now, let's go to new dream. And this allows us to enter in a string. So first it asks how long is your dream? Basically, how much data are you going to provide us? We scan that in, we allocate that amount of memory, and then it asks us to actually give the contents. And then we read those contents in to the address that we just allocated with malloc. And then we store that at whatever the current index is for the array, and then we presumably increment. Yeah, we add 1 to index. What is sizes about? Oh, so we have 2 arrays. that are tracking stuff. We have one array that is tracking pointers to the strings or whatever memory we have provided to the program. And then we have another array that is tracking the size of each of those strings. That makes sense. Okay. Because then when we want to read it out again, in theory, it would need to read this, like whatever size amount of bytes, and print that. At the same time, we actually don't see, like, the read function is not checking the size. It is simply using the address of whatever the string is, or doesn't really have to be a string is the key here. But whatever memory we have provided using the write function, it's going to print it with printf. And printf is just going to keep printing data until it gets to a null byte. So if we provide data that does not end with a null byte, then it will potentially allow us to keep reading memory beyond where we should be reading it, I think. Is it man2 read? Okay, so we call the read function. Let me just double check that this is not going to put a null byte on anything, because it's just read data from a file descriptor, in this case like standard in. But because it's not really a string function, because maybe you're reading from a binary file or something, it's not going to null terminate the data. So we can provide stuff in the write function that is not null terminated, and then when we read it out with printf, it'll read past the end of that however many bytes additional until it hits a null byte. So that's interesting. I don't know if we need to take advantage of that, but potentially we could. What else do we need to accomplish? I mean, we need to like pop a shell. So how do we want to So what we could do is use the edit function to modify memory. So the write function doesn't take an index because it's just add a new entry. So it presumes that you're adding it to the end of the database, to the end of these arrays. The edit function is most likely going to take an index because it wants to know which thing you are going to edit. And if we provide an index such that we are editing the global offset table, then what we could attempt to do is override the location of the global offset table entry for, let's say, printf, the one that we have here in the read function. We'll switch out printf for the system function, which is the function that lets us run a command, and so we could run a shell, and then we have access to the shell. We'll switch that out, and then when we call read, if we provide the index of a string, of an entry where we added the string like /bin/sh, it will end up calling system with /bin/sh as the command. So I think that's what we want to do. We're going to need to first read memory. We want to read the address out of the existing printf function address. We might need to call read once first, Oh no, because we call printf here in the main function, so that's fine. So the issue is if you're using the global offset table, it doesn't put the address in there until the first time you call the function. But we will have called printf already before we finish our menu stuff. So we will first use the read function to read the value which is at the address for that global offset table entry for printf. That'll give us the real address of printf, which is leaking a pointer into libc. Because we don't know where libc is going to be stored at memory due to the ASLR protection that the operating system has, we need to leak an address that is within libc, and then we can do some calculations on it to work out where the system function is relative to the printf function. Once we calculate that, then we use the edit function to overwrite that memory location with the newly calculated address of system. Then we use the write function to write an entry with /bin/sh. And then finally we call read, and we say read that entry, and when it wants to call printf, it ends up calling system. So that's what we can do to accomplish our exploit. So I'm going to go ahead and use Pwn tool to do this, as I have on all the other streams. And we'll say binary is an ELF file named dream heaps. We will read in that file for the binary. We'll say printf got address is binary.got printf. And we also need libc, which you can just grab from here. And then we can say printf, let's call it libc printf is libc.symbols printf, and libc system is libc.symbols system. Okay, and then we also know heap pointers, or like say pointers array is at, where did I have it? Calculate this address earlier. And then what we need to do is calculate is pointers array minus printf got divided by 8. And then we want to run our program. And we'll say target.receive until something. We're first going to read memory, so that's 2. And the index we want to send, we'll receive something. And then we're going to send printf got index. And we want to say target.receive n8. call these offsets. Okay, so now we've received the libc printf address. And we can say libc system adder is going to be equal to libc printf adder plus libc printf offset minus libc system offset. I think that's correct. Do it that way because I think system is earlier in our libc. You might need to switch these around. Let's do it this way. So if we take system minus printf, if system is earlier, then this will be a negative number, so we will subtract it from printf. If system is later, then this will be a positive number, and we're going to add it to printf. And so the calculation will be correct in either scenario. So that'll be our libc system adder, and then we need libc, and then we, oh no, that's fine. Now we're going to receive until the next menu prompt. We're going to say edit. Let's call it dream, because technically writing a dream is also writing memory, and editing a dream is writing memory, so I just want to call it according to the menu options. And target.sendLine string printf got index. And oh, let me look at that. Because I wonder if, you know, I was sort of assuming that I could write the value that is at a particular index in the heap pointers, but I don't actually think that we can. So we get the whatever the index is, we move that into Rex, store it, and then write into it. Where is RDX? Okay. So as much as we can leak any random location in memory that comes earlier than where the data structures are stored, we can't necessarily just write any random piece of memory because it's going to write to locations on the heap which are mallocked. So unless we can figure out how to That's going to be interesting. So really what we need to do here is provide an index to a location which has the address of the printf GOT entry as its as the memory there. So we will index into heap pointers, and if the value that we get from the indexing of heap pointers happens to be a piece of memory which has the address of the printf GOT entry, then we can make use of that. And there's maybe a couple ways we could do that. It's possible that the PLT stuff has that address in there because it needs to read from that address. It's certainly possible that the code it'll have the address of the PLT. So maybe the PLT would have that address, but it's not really guaranteed to be aligned. We could do a couple different reads and a couple different edit writes to no, because it would need to be 8-byte aligned or the read stuff won't work. So I don't know if that's the route that I want to go, is to try to find it already within the binary that it happens to have the address of the printf GOT entry in there. I think what I could do is one of two other routes. One is we can write an entry and put the GOT address directly as the contents of that entry. The difficulty with that approach is that the location where that memory is written is not determined by us. It's put on the heap when we call malloc. So it is not necessarily consistent from one execution of the program to another. And I think the heap has a random base address. Like, basically, I don't know that we would know where to find that. Oh, okay. So that might be the way to go. Let's say I think we can use all the same things that we were just talking about using, but we just have to do a couple iterations of them. So let's say we write a first entry into the dream array. It mallocs the space for that entry. The data that we're going to put at that entry is the address of the printf GOT entry. Then what we do is we call read, and we read the we need to have a pointer to the heap pointers array. Ooh. Is there a solution there? It's possible. So I'm starting to feel like each time I think about how to do it, I'm like, oh, we could do this, but then it's more like, oh, but in order to do that, we need to be able to do the same thing that we are just trying to do. So it's a like they say, like turtles all the way down kind of problem. It's this recursive issue of depending on being able to do the thing that you are attempting to accomplish with the technique that you have. Or I'm really explaining that very poorly, but it's like, in order to get to the tree, I need to first get to the tree. I guess it's like maybe a catch-22 kind of thing. I'm not certain that it's impossible. I haven't played it out far enough, but we would need to have an address. We need to have a location in memory that has the address of heap pointers. And certainly that is within the code in certain locations. but I don't know if it is 8-byte aligned in any of those locations, which will be necessary. So that might not be the one to start with. If we can get away with it, the thing to do might be that we can control the value that is in the sizes array. Because when we add an entry, it says, give me the size of the entry that you're about to provide. And then we can provide, it didn't seem like it was concerned with like limiting what that size is. So we could say the size happens to be exactly the same as the address of printf GOT entry, which is going to be a really huge size. And hopefully we don't actually have to provide all the data for that, but I don't know for certain. But if we can provide the GOT entry for that, the address of that GOT entry for that, then we know at offset 0 or offset whatever within the sizes array, which is a fixed address, we know that's going to be the address of the GOT entry now. And we can use that in our read call or in our edit call, assuming that sizes is earlier than heap pointers. Oh, I guess I can just look at this. So, but it is not earlier. I wonder if maybe we can provide enough entries that, because these are very near to each other. Oh, and these are 4-byte pieces. Okay, interesting. So heap pointers is at 20A0 and sizes is at 20E0. So that's an offset of 48 bytes, which is only translates to 6 entries, I think, before we start overwriting the size. So let me save my exploit, and I'm just going to try that by hand because there's not that many entries. So we've done 1, 2, 3, 4. Or this one's going to be 4. No, we've done 4. Okay. 5. And now if we say read the first entry, no, it hasn't overwritten it. Maybe I'm mistaking the addresses somehow. Oh, is it for edit? Oh, sorry. Okay, so I do think that like there's not really much in the way of indexing checking on the maximum side, and since this should be, it's located 6 entries worth of space prior to the sizes. After 6 entries, we will start overwriting the sizes array. There's not a lot of visual or output that we can see from the how to put it, from the program itself to know that we've overwritten the sizes array, but it feels like that's pretty clear what's happening. So if we can overwrite the sizes array, and it's going to be overwriting it with pointers to whatever memory we've mallocked. What do we want to do with that? So we don't get a new size when we edit. We don't get to rewrite the size, because that would allow us to control where the heap pointer entry actually looks to. But it keeps the size that's in there. At least I think it does. Let me double check that function. Am I in edit already? Okay. Yeah, it just reads size. It doesn't actually write back to it, I don't think. EAX gets stored in 14. Hey, Julian. I got your Whisper, and I have downloaded that challenge, so if I can get through this one relatively quickly, I'll try to work on that one on this stream as well. And then it null terminates based on whatever the size we already had was. Okay. So maybe we can use the delete functionality. I just call free on that, huh? All right, I'm going to take a break for like a couple minutes, and then we'll come back to this.
Just walk right out the door. Don't want to do this anymore. Now I'm lost without you. You drive me crazy out my mind. How'd you do this every time? Now I'm lost without you. You used to be the one I talk to when I'm sad. Can't you see now tainted love is all we have? Our issues run so deep, now when I try to sleep I feel so bad. I should leave, and by the time it's done I'll be
All right, I'm back. Still reviewing the delete function. It's pretty straightforward. We take the index and we find a 8-byte chunk of memory based on that index, offset by heap pointers. Has to be however many entries we've added or fewer, including negative numbers, to do out of bounds access. Then we call free on it, and and then we overwrite that location with 0. That location in the where, like, whatever location in memory we just read from and did the free on. So, I mean, we could call free on any old place in memory. I don't think that necessarily helps us. At least there's no obvious thing from that, unless we have to do a real heap exploitation on this. But I think this is mostly about array indexing. But one thing that we could look at is, right now I think we have overwritten the first value in the first 2 values in the sizes array. And if we free them, so if we free number 7, index at 6 rather, because it's 0 based, then that should write 0 to those 2 locations in the sizes array. And if we then try to edit those, it should call read with 0, which probably won't allow us to send any input. And that's a way that we could test that the overwriting has actually happened. So if we delete entry 6 and then we say edit entry 0, no, if we say edit entry 0 and say another test, and we then read entry 0. I thought I hit 2. Oh, I'm in. What am I in? What is this situation we've gotten ourselves into? Oh, maybe that's because the read is on reads with a length of 0. I don't know. I definitely got it into a weird, messed up state. So the fundamental issue is that we need to be able to have the address of the printf GOT entry in memory somewhere. And that location in memory has to be within the array of heap pointers or prior to it in the address space. And it has to be 8-byte aligned. So I imagine if we run it and we look at the VM map, the address space where our indexes are is just this segment, and then the heap is after it. So And those are the only two writable ones that we will know the addresses of. So the heap is actually not at random locations. Although I guess it's possible that the, how to put it, it's possible that malloc will allocate within that space somewhat randomly. But if it's not, then it's probably allocating at the beginning of that space as soon as it can. And, you know, this is a very simple program. There's probably not a lot of mallocs going on prior to the actual challenge code. So we might be, when we call malloc, we might have it right at the beginning of that area, in which case we could, in theory, provide enough entries that one of the addresses we trying to think about how to accomplish this. So if we write enough entries to overwrite into the heap, then let's say we overwrite the first thing on the heap, and maybe we put 8 bytes in there for the address of the printf GOT entry. We're going to end up overwriting that with the address of another malloc call. Fine, I think we can live with that. But then we can edit it, and it will rewrite and we can rewrite the address of the printf. I mean, we wouldn't have to write it the first time because it's going to be overwritten, but when we do the edit, we could rewrite that memory with the address. And that is then going to be also the location of one of our entries in the heap pointers array. Heap overflow with a fast bin attack. I don't know what fast bin is. I've heard that term. I don't know if it was you that was using it or I saw it in some other scenario, but I don't actually know what that refers to. I don't think we need to do any kind of heap overflow. It doesn't necessarily look like there is a means for doing a heap overflow, because when we add a new entry, it asks for the length of that entry, it mallocs that amount, it calls read, and then I thought it sets a 0 on there, but I guess it doesn't, because that's what allows us to be able to put in a value. So it doesn't null terminate the memory that we've written into the location that's been malloced, but it does limit the read call to only that size. So the read won't overflow the mallocked amount of memory. But we could overwrite that memory by writing so many entries into the array that the location of heap pointers, which is where we store the addresses of all of that mallocked memory, that array of pointers could be large enough that it starts going from 602 whatever into 603 whatever. We'll have to see how many that would be. 3000 hex minus 20A0 hex is almost 4,000 entries. So if we write that many entries, then I think the addresses that it's storing for the malloc memory are being written to the locations of the first bits of memory that it malloced. Meaning when we read those, when we try to dereference the address from the first entry, it will read now the data that it will read the address that we put from malloc for the 4,936th entry. And then we can overwrite the value that's there because we can edit our entry. And basically the first pointer in our pointers array will point to the address where we have stored the 3,936th entry in that same array. And so when we edit the first entry, we will overwrite the value that's stored at that 3,900 whatever entry. So then when we say read the data at that entry, we have controlled what that pointer value is, so it will read whatever memory we want. Or if we say edit the data at that entry, we again have controlled that pointer, so we can edit arbitrary memory. And then we can use that to edit the GOT, assuming that the thing that we put into that spot was the GOT. I think so. Okay. Let's confirm some stuff. So I want to see what we get back from malloc. So we'll say new dream plus 70. And we'll continue and we'll hit 1. And we'll say it's 8 bytes. And now it's going to malloc 8 bytes. And RAX has this address, 603670. So it's actually giving us quite a bit further. So we would need 5,584 entries to ultimately overwrite that bit of data. Okay, I want to rerun the program and see if that is still the same case. And we did get it consistently. It's consistent in GDB. Let's try it as we load it from Pwn Tools. So let's send 1. I guess we can do that. Okay. I didn't need to exit GDB. I want to set that breakpoint again. And let's, okay, so we're paused, so we're going to attach to 2244. And continue. Why did it? All right, I guess I do need the pause again. $22.54. Okay, so now we got malloc, and we hit NI, and no, it's randomly located. So that's not gonna help us. That's my bad. It's just I was looking at the address. At least I don't know if it's necessarily randomly allocated. We can definitely run it again and see if it's the same address, but even if it's not, if it's always at this address, that's like so many entries. I don't want to. I mean, you know, it's like we could write a script to do it for sure, but it starts to feel less like what the intended solution is. If we yeah. So what we could do is the earlier thing that I was thinking about, which is the sizes thing. Does that help us at all? I guess not. What happens if we say 0? All right, I'm gonna try some stuff. We can just exit after this because I don't need to. Okay, so we're gonna run it one more time. 2262. And yeah, completely different address. Okay, so the heap is randomly allocated. I don't know why I got tripped up thinking it wouldn't have been, but of course it is with ASLR. So the next thing I want to check is what does malloc do if we give it a 0 instead? Oops. All right. Then it does allocate memory. This time we got another heap location that, I don't know, sometimes it's very close, sometimes it's not so close, which is interesting. But I don't know that I want to rely on it because it's still going to be somewhat random, even if it happens to be very close. So mallocing 0 bytes seems like it still does that. If size is 0, then malloc returns either null or a unique pointer value that can later be successfully passed to free. Interesting. Well, it didn't return null in this case. So I'm wondering if 6BA was the start of that, and it did 6B B270. So basically 1 270 offset from the beginning of the heap. And I think that's kind of what we saw in some of the previous ones. 7 270. I didn't look at the heap at that point though. So for this one, it was at 1 270. Yeah, so it's the same offset. So I don't know why malloc like gave a pointer. I mean, maybe it doesn't have to be a pointer that can be used. It just has to be a pointer that can be passed to free. So, maybe it puts a little bit of the tracking data just prior to that location, so it's technically an entry that free can work with, but it doesn't need to do anything with the malloc free list or anything where it's tracking what memory has been actually allocated. I don't know. So passing 0 doesn't help us there. I guess I can resort to trying to figure out where we have an address of printf. I mean, we have it in our code. We have the call to printf right here. And this is going to call the PLT entry. Oh no, what was the thing that I wanted to do? Could try that with the sizes, with the editing the heap address. Let's try that. So in order to edit a bit of memory, we need to have the pointer to that memory address stored somewhere in memory already at an address that we can control, or that that we know of, and which is located basically at the very beginning of this section or in one of these two sections. So if there's a location in one of these two sections or right up at the beginning of this section where we have the address of the place that we want to write to, and that address of the place we want to write to happens to be 8-byte aligned, we can calculate the right index as a negative number and specify that when we say edit, basically, and that will allow us to edit that bit. It'll check the size of how much we want to edit based on the that same location in memory, but offset by 48 bytes. So that is a factor. But in theory, if I can find in the in one of these first two sections the address of the printf GOT entry, which is this value in hex. If we can find this address, interesting. So the GOT is immediately prior. No, how is that? Yeah. It's a little bit prior, sorry, to the array where we're storing all of these pointers. So again, we need a pointer to this, like we need this value in memory as 8 bytes. I don't know if we actually will have that, but we can search for it. Let's see, so we want find a giant starting from here going to here I didn't copy that, I guess. Okay. And it's really through like here. That is going to have this value. Couldn't, oh, I need to maybe attach again. Why couldn't we access that memory? It's the same addresses. Just take off all the extra zeros. But I don't understand why it doesn't want to search memory. Maybe it's because it's trying to search in the like after section. So we could do up through here. Nope, still doesn't want to search that memory either. Huh. Well, let's search the readable section. See if that works any better. Didn't find it in there. Okay. Do you have the non-giant? It's just a word? No. Okay, so if we don't have that value in memory, do we have this value in memory? No, okay. So, I mean, basically we need to put that value into memory, but we need to put it into memory at a location that we will know where it is. And that's very tricky. And so my thought is we could put the value into the sizes array. Because we know where the sizes array is. The problem is that the sizes array is located after. Oh. So if we add a new, no, damn it, no, okay. Where is index located? 8C. So it's located before. So the idea would be like, okay, we can put 2 entries into the dream array, and that will write a value into sizes that we can just specify. It takes that as a number, puts it in as a D word into a fixed location. So if we do 2 entries, then we can write a full quad word value into there. That's fine. We probably just need the low D word, because the high D word is going to be 0. However, when we try to say edit using that location, the the edit is going to check the index number, and since the sizes array is after heap pointers, like the index that we'd have to give is a positive number, but it's going to be larger than the index maximum that is tracking in this entry. So it's not going to let us reference the theoretical entry that happens to fall on the beginning of the sizes array where we have entered our data. Pretty sure. Let me double check. Yeah, we check that index. And if we write a bunch of entries so that the index is high enough that heap pointers plus whatever offset is the one that ends up talking about the like where it overflows and overlaps with the sizes entry, the first one in sizes, we will rewrite the value that we put into sizes in the first place, because it'll call malloc, it'll get an address, and then it'll store it at that location. And we can't later go back and change sizes because we just don't have a way to change it, basically. I guess and I like the deleting of entries. Oops. Interesting. Deleting the entry doesn't impact on index at all. It just frees the memory at that address. So how do we get this value into memory at a location, at a fixed location that we know where that is? So we have relatively arbitrary capability to leak addresses that are actually what we can leak is data stored at places where we can reference the address to that place. So we can't just say, read me the data that's at this location in memory. I can say, read me the data that this location in memory has a pointer to, which is, a pretty significant constraint on the earlier the other capability of reading any location in memory. Because then I need to have a pointer to that location in memory at a fixed place that I know of. So finding the how do we leak something useful? I mean, one thing that we could attempt to do, I don't imagine that it's going to be that helpful, but like we have a %d, we have a format string that it gets used by scanf. And if we pass the address of that format string, basically if we calculate the right index so that this is the address that gets passed to printf, it will leak a stack address, or it'll leak whatever piece of memory is like next to it on the stack. I don't know, again, that we get a lot of value out of that. So how do we find a location in memory that points to something useful? I'm just start writing some notes, I guess. I don't really care about this stuff. So, new dream. Let me put this in a different file. Oops. New dream. Take size, OData, mallocs, that amount, reads into the buffer returned by malloc, stores buffer address in heap pointers, let's say. stores size in sizes. Read dream takes index, calls printf of heap pointers plus 8 times index. Edit dream takes index. Reads into buffer using address from heap pointers time plus 8 times index. Okay, so those are the 4 things that we can do. We can provide a size, malloc that amount of data, read data into the buffer address that malloc returned, store that address into the heap pointers array, and then store the size that was provided into the sizes array. And we don't get an index situation on that. Like it just uses whatever the current value of index is and then increments it. So we can't use that to just write the size into a particular location or write the malloc return address into a particular location, or an arbitrary location like out of bounds. At least it will throw it into the buffers, the address, the arrays for those particular pieces of data that has already been established. There's a sort of overflow situation with the arrays in that if heap pointers has more than 6 entries, then on the 7th and later entry, it's going to store its address into, okay, so if the location of heap pointers is about 48 bytes prior to the location, exactly 48 bytes prior to the location of sizes. Since each entry in heap pointers is 8 bytes, that's 6 entries that it can store before overflowing and overwriting the values that are in the sizes array. Okay, that doesn't actually help. The O that I was thinking of was after writing the address returned by malloc into heap pointers, and if it's on the 7th or later entry, then it's overwriting the value that's in the sizes array. After doing that, it then writes the size value. The problem is it doesn't write it to that same location. It writes it to sizes plus 7 entries or whatever. However, sizes is 4 bytes. And heap pointers is 8 bytes per entry. So maybe I can do some math and we can figure out a point at which writing a new entry overwrites an old entry for heap pointers with the size value for the new entry. It'll overwrite the low D word of that first, at least. We could do a second one and overwrite the high D word if we needed to. Yeah, maybe we can use that. Just the fact that heap pointers is going to grow twice as fast. So let's do a little diagram. So we will have heap pointers. So let's do this as like 0, 0, 1, 1. So those are our first 6 entries. We can maybe say is that 6? Yeah. Then we've got maybe I shouldn't put in the, it's gonna mess up the spacing a bit. Okay, so this is sort of my little diagram. As we put in the first 6 entries, these are the numbers for the offsets. So I guess we could do it like this. No, I like it with the double values because I don't think we're gonna need to put so many to overflow 16, let's say. So we put in 6 entries, indexes 0 through 5. That fills up heap pointers, whereas sizes, and it goes right to the end of where, before it starts overwriting into sizes. Now, if we put in 6, 7, 8, 9, A, and then B, and C. So after 12 entries, or 13 entries because we're 0 indexed, the 14th entry, the low D word of the heap pointer lines up with where we will write the size to. And so if we put in a size that we control, since it is written afterwards, S. Since we actually store that into size array after we store the address into heap pointers, then this value for C will get written over the heap pointer's value for C. And technically we have that overwriting happening with B as well. But it's happening in the high D word of B, and I don't think that's what we care about. A is overriding B, but it's happening prior to B. Like, the A value gets written and then the BB value gets written, so that doesn't help us. BB gets written and then B for sizes, but it's only the high D word. So then we can control what value we have in the 14th entry by putting the correct size that we need for both the 14th and 15th entries. Maybe we can just rely on the high D word being 0 and don't have to care about the 15th entry. Otherwise, we might have to write it and say that the size is 0. And that should still maybe work. I think the problem is that it might mess up the read call that happens before we do all that storing of stuff into the arrays. Because it does seem like, let me save my notes. If we run it and we say write a new entry and it's 0, yeah, maybe. And then, no, okay, so we can put 0 if we need to. It doesn't mess up the read call. I don't know why stuff got messed up on an earlier run. I thought it was because I was providing 0 as the length to read, but it just doesn't try to read anything, and that's fine. So at that point, we have controlled the address of a pointer. We've controlled a piece of memory that we know the address of. It's at a fixed location. It is also within the area that we can edit and read from. So we can use that to read. If we put the right size in, then we can control that location to have a pointer to the printf GOT entry, and we can read from it. It'll use that pointer, so it'll read from the GOT entry, and we can pull off the first 8 bytes. That'll be the actual address of printf. So we'll leak the printf address, then we can say edit, and just straight up edit the GOT entry because we can actually access that by negative indexing. So I think that's all we need to do. That might work. Might actually work. Okay, so what we need to do is provide uh, 13 entries, and then on the 14th is when we can override. So I think we can provide a length of 0 for those, and then target.sendLine1, and now we need to say pack 32 of, or no, we just need to present this as, what happens if I do string of printf GOT okay, and then we gotta present some kind of content. So now we can go back to target, and now we're back at the menu. And the nice thing is the content gets written before we do the overriding of the heap pointer, so we don't have to worry about like accidentally writing to the printf GOT entry. Although I guess maybe that wouldn't even, like, that would just simplify things a little bit rather than being a difficulty, but we don't, that's not what's happening, so we don't have to worry about that. So now we can read and I think we need to say 13. Is it 13? 10, 11, 12. So this is actually the 13th entry. What do we have, right? It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I don't know why I was talking about 13th and or 14th entry. So now we can say printf libc printf adder is target.receiveN 8, and we'll read that. We will say edit. We're going to edit the entry that is the 12th entry. So we can edit the printf GOT, and we need to do libc system adder is libc printf adder plus the difference of system and printf. And hopefully we can say send line P64 libc system adder, and then I think oh, let's do let's do a first one. I guess that can just be a string. So we'll send /bin/sh null terminated as the first entry, and then we will do another 11 entries that are rather another, yeah. So we need 12 entries first, then the 13th entry is where we do the overwrite. And then I think to trigger the actual call to system, ooh, that's going to be tricky. Hopefully shouldn't be an issue. I remember that we call printf here for whatever reason. So that would end up getting called like that would end up getting run before we end up running the read dream, which is where we really want to trigger system, because we can tell it to read the entry where we put in /bin/sh, and it will call system with that string or with an address pointing to that string. But I think if it calls system here, that's just gonna fail. I mean, it'll call system and then system will come back and be like, I don't know what that program was. There's no quit program. And we'll probably just continue. So hopefully it's not an issue. If we go to edit dream, it's not like it calls printf elsewhere. So, okay. And then read entry 0. Okay. So that's all of that stuff, but I want to put in the receive lines stuff. Let's see. Just making it a little more generic. And then probably need more. Okay, let's say I do okay. So yeah, I think we're good then. Let's give it a shot and watch it not work. We're receiving until that on line 27. Interesting. Why wouldn't that? You know what? I'm not even going to put in the null terminator because it seemed like it was getting null terminated properly. Okay, well, we got past that. Cannot concat into bytes. Use 64. Oof, oof. We are printing out /bin/sh, but it hasn't overwritten the address that we thought it was going to. Oh, You could define some functions to make it easier. Yeah. I mean, I don't know that I need to be doing it that often, but you're right. It's like we are sort of repeating the provide input cycle. Let me double check my logic of this. Kind of feel okay with it, but it's obviously not working. So we're going to run it in GDB. Two, 3, 5, 1. Then where do I want to put my breakpoints? Want the breakpoint on new dream when we are going to store into sizes, which is just before the add 1, 2 before it. This one, okay, at 143. All right, so in this case, EDX is 0, that's fine. RAX is 0, and EDX is 7. Is /bin/sh? Oh, yeah. /bin/sh is 7 bytes. It's 8 with the null terminator. Okay, that's fine. Then the next time it is 0 and rax is 1. Go through all these till we get to, this is the last of the padding ones, I would say. And now this is the address that we are going to attempt to store RDX with. This is the size into entry RC. So let's just double check if we new dream. So this is where we are storing into heap pointers, which is RAX times 8 plus this address. So can we look at what that is right now? We do okay, it's got that address, I guess. I don't know if that's the heap is, or it looks like maybe 7C1. This section, maybe this is additional heap that it is allocated. I have no idea. Don't know why. I presumably that's the address we got back from Malik though. Because like yeah, okay. So that's the address that we got back from Malik, where it is stored on the stack, and then we have thrown that into this location in the heap pointers array, and then Rax is not being changed, right? Or I guess it is changed, but it should be the same as it had been when we did this, right? Because they're both just whatever value is in index. So now if we look at this address, do that. Do it this way. Why is that 602 110? Is my math wrong? E0 and Rax is C, so C times 4 is 30. 30 plus E, or E0, should be 110, yeah. Then 8 times C, maybe I did my calculations wrong then. 8 times C is 60. I could have just doubled that, yeah. 60 hex plus A. Yeah, we are off a little bit. Okay, that's my bad. Need to check my notes again. So, real quick, let's do it the other way. So that's 40 hex, which, oh, I was thinking it was 30 hex. That's my issue. So we need this to be, so this is at 30, that'll be 40, assuming 4 bytes per character in this diagram. So really this is where it goes. just go back to that. Okay, so I guess what we need is the 16th rather than the 13th. Okay. We do this as like overlap entry -1 -1. Whatever, I don't need the explanation. I know what I'm doing. I'm a very smart guy. That's evidenced by how often I get these things right and do basic math correctly. You know, we can take out all these -1s. Doesn't actually help us anything. Okay, then in theory, we're closer to a working exploit. So we got this on line 49. The one after we send read, don't receive. Can it not read that address? I just got EOF. Oops, I didn't mean to run it again. What do we print? We get segfault that time. Okay. What are we? Is that line 30? Has a problem with this one now? What? Why is it failing earlier now? I didn't. All I did was add a print. If we take out that print, how does that break it? How does that make any sense that it breaks up here if we put a print around this? There we go. Okay. Stopped being an issue. But what it is printing out after we provide that entry number, are we somehow on the wrong? Why is it breaking sometimes? Maybe it's random. we can definitely have this stuff time out. See, now, yeah, it probably would have been better to write a function for this, because I'm changing stuff in all these places. Whatever. Okay. So we get the prompt. We're not actually printing out the stuff in the prompt. I guess we're printing it down here. So we get the menu. I'm printing it. No. Didn't decode one of these. Why is it so many? That's too many. Let's do so. I think we can say then menu option 1, length of the command, and the command itself. Let's do the debug stuff up here. Okay, so then let's do it this way then. Okay. And this, or just replace it with command 1. Doesn't really matter. Or, sorry. Maybe we can even simplify. Let's just go full writing a bunch of code because we're already this far into it. Okay, then now we want command 1 and printf GOT as the size, and let's call it overwrite as the content. So now we want command 2 and what do we want to do here? In theory, I'm going to read the value from overlap entry and going to receive all. That's an issue. We don't really want to do str on this last one, huh? Which I think is fine because we're just directly presenting strings for the other ones. Sure. And say command 2 and 0. That should be it. Okay. So obviously stuff's a bit shorter now. We can figure out why it's breaking maybe easier this way. Invalid syntax. Right, we don't have any end-to-end. What did I do here? String is not... Oh. No, we got a sig fault, but it did seem to... Now, why are there so many entries? Why does it repeat like this? Look at this. I don't know how many entries this is. So let's try it like real short like. Okay. Allow none for both of them. It doesn't really matter. All right, so first things first, we should write a dream. How long is it? What are the contents? Okay. And then command 5 from the receive until... Oh, yeah, because we sent in... Okay, but my concern is that... Why isn't this one happening? Oh, because we need 2. Okay, so we get 3 entries from that, or 2 entries rather, in the last menu cycle is now with 3 we get this infinite so I mean we can just manually recreate this on the terminal, but we're not doing anything different but trying to do a second padding entry. Right, just reviewing the code, making sure it's not anything very obvious that is broken. Okay. So I say 1, 7/bin/sh. It's a new line. I say 1. What is it? 4 test. 1 4 test. Like, it doesn't seem to break at this point. Right, 5, that's puts us out. So let's double check. One, two, three. Okay, that's presumably the right number of entries now. So, you know, let's go interactive after that. And why is it stuck on, and we segfaulted from that? Okay. Oh no, this one went the infinite scroll as well. Why? Any ideas? Those of y'all in chat? Having some difficulty understanding why providing this amount of input is breaking it. Let's do 1. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 1, 8, no. Then we want the size to be, let's get the address of an actual string that we have in memory. This string, the %d. So we'll just print, oh, but it's a format string. Let's have it print out the Dreamcatcher string again. So we'll provide that in decimal form. And then we say 2, and we give 15, and then 5. So now, if we again, it just loops forever. So what is going on when we overflow. I guess, I mean, why am I going through all this trouble when I should be like looking at it in GDB? Okay, we'll pause and then what is the 2572? What do we care about? 143, I guess. So EDX is 7 for the lengths of bin sh. Okay. We'll just continue. Now it's 4. Why is it 0 for the entries? We gotta from U64 output in. Why did that happen? Like, why are we already? Oh, because of the timeouts. Okay, so let's do like debug. Otherwise, timeout equals 1. Okay, and then we should also if debug. That way we'll wait forever. 2588. What? I expected. Oh, I switched those the wrong way. What? Is timeout 0 by default then? This is the problem with trying to write computer code. I'm not good at it. Timeout is 0 by default. Okay. None. And now why? Okay, let's set a very large timeout. 60 seconds times 60 minutes. If I can't finish a debugging session in 1 hour, then I'm not going to be very successful Or I haven't been very successful in debugging this, I guess. Okay, so EDX is 7 for /bin/sh, and Rax is 0. What's going on? Are we now going to wait an hour for correct input? We're on receive until line 27. Well, I mean, I guess that is helpful to understand. That something went wrong with how we are. So the last stuff that we output was how long is your dream? And you're starting with reverse engineering in 2 semesters and it looks confusing. Hi, Gangton Spanked, and thanks for the follow, Cerebro11, and for the follow earlier, Gangton Spanked. I appreciate it. I mean, what I would say is, like, don't get discouraged. This stuff is not necessarily introductory level reverse engineering, and my experience is what looks like very complicated stuff becomes very, much more tractable as you continue to work on it. I don't know if you've done any like software development, but if I think about when I started learning about programming and the students that I've taught programming, like, you always start in a position where everything looks like gibberish. And then you sort of progress to a situation where stuff seems to look like a thing, and you have ideas about what it's supposed to do based on a certain reading of the code, let's say, that isn't necessarily the deepest level of understanding of like what that code really means. But so, like, some of the students that I've had, they go from none of this makes any sense to, well, if the variable names make sense to me, then I can sort of parse out what lines are supposed to be doing based on the variable names. But if they were all gibberish variable names, for example, then I would have no idea what the code is really trying to do. And then eventually you can sort of progress to, even if these variable names were all random, I could work out what the code is doing. It would take longer. But that's sort of like, reading code and reverse engineering are the exact same thing. That's the secret they don't tell you. Being able to read code and being able to reverse engineer a program are the same skill. We just use that term when the code that you're reading is assembly or machine instructions or, something at a certain low level and below, or is otherwise obfuscated in a way that humans aren't supposed to be able to read it. But the skills involved are the same. If I get a chunk of C++ code from a project and I don't understand the context of that project, and the variable names are in French or some language that I don't understand, so the names of everything and all the comments that might be in there mean nothing to me, that's the same as though it were obfuscated on purpose. And so, you're practicing the same skill. So I would say, don't get discouraged, because you just, you keep you'll get incrementally better the more you do it. Yeah, you had C and some very simple assembly code in operating systems. Cool. So, I mean, I think you're in a good position to work on that stuff. I am, this variety of using reverse engineering in the effort to build exploits and take advantage of security vulnerability kind of stuff to do these ponables challenges is a very particular way of using that skill. I also do reverse engineering that's a little more general on various programs, and it's a whole different mindset in those cases. So the stuff that I'm doing right now might seem very like it is. I don't want to say necessarily more advanced, but it's just like it's almost more niche and more targeted at a very specific kind of reversing and understanding what might be happening in memory when the program runs that shouldn't be happening. Whereas if you're reverse engineering a program to understand what it was intended to do, that can be a lot more straightforward than reversing it to understand what it wasn't intended to do, but actually could do, which is ultimately the mechanism of the finding the vulnerability and trying to come up with an exploit. Is like, oh, the program can do this even though the coder did not intend it to do that. And I think that's, that adds another layer to the thinking rather than let me just try to figure out what the coder intended this program to be doing, because you can read the intention of the code a lot easier, I'd say, than you can read what they didn't intend, but technically the compiler output to do or whatever. So like when I start off looking through some of these CTF challenges, I can read through what the general idea of the program is right away, but it takes a lot more work to dig in and find where is the flaw in their intended design, and how then can I arrange a circumstance that exactly controls the flaw to do what I want. So yeah, if you're just starting off reverse engineering, this is going to look very complicated, and it is a little more complicated than usual stuff, but you can get there for sure. You started CTF like 2 days ago, did all the bandit levels on Over the Wire, and I'm doing the Leviathan now. Nice. I did bandit a little while ago. I don't remember if I got through all of it because there's just a bunch of levels in there, but some of them definitely taught me things because I didn't know there's like a few Linux commands that I hadn't learned about or had reason to use or something that came up in one of those bandit levels, and it was just a nice little trip through stuff. And if you are, especially if you're newer to sort of the Linux side of like I don't know, you could call it system administration, but just sort of using the system and taking advantage of stuff from that. And then especially if you're new to general CTF challengey kind of things like encoding stuff in base 64 and all kinds of stuff of that nature, it's a really good kind of introduction. And I haven't yet gone on to the other stuff on Over the Wire, so I don't know what's in Leviathan. You came to level 25, 26, but you're not sure if the server doesn't work or my SSH is wrong. If I had to guess, you probably have something wrong in your config. I don't remember enough. It's been like many months since I did it, so I don't remember what level 25 and 26 were about. But, I mean, I don't think I encountered anything where it was like, oh, the challenge is broken. Granted, it could have broken since then. Yeah, and have you made sure that the permissions on that key file are correct? Because SSH is very particular. It needs you to be able to read but not write that file, and for nobody else to be able to read that file. So I think you got to set 600 as the permissions, the octal permissions. But usually it will give you an error message and say, hey, the permissions are wrong, I don't want to use this. Will I cover the binary you sent? Probably on the next stream, because we're getting close to when I really have to end it for the meeting that I have, and the stuff that is going wrong with it right now, I don't understand enough to be confident that I'm going to figure it out in this moment. I'm going to take out the timeout stuff because I feel like that's just causing me problems at this point, and see if that helps at all. But yeah, I'll probably have to get to yours. I don't want to start on something, on a new one this late. So I'll start on yours at the beginning of the next stream, or I'll maybe keep that in. Why is, see, I don't understand what the fuck. Maybe not start at the very beginning of the next stream, just because I know people aren't necessarily around for the first half hour at least. I might start on a different challenge or continue on this one if I haven't fixed it, or finished it rather, and then let me know when you're around and I can start on it then, because I'm sure it would be more interesting for you to be able to see me go through it. Let's try to understand what is going on. And also, 0xraf, thanks for the follow. Online Dreamcatcher, right? We print the menu, and then why does it not? Oh yeah, that's the first prompt for. We have debug should be on, so we should print everything up to there. I guess the issue is let's do it that way. No. Is there? I don't know. Just repeat these. So need to get more info on. Of course, that was not the I want to attach. And we're going to continue from there and run it. So what are the contents? Okay, now we hit the thing. That's good. Now we're hitting it. I don't understand what was going on. RDX is 4 for test. Okay. Then we are 1 too early, because this is RAX is F, and I want RAX to be 16, I'm pretty sure. So I want it to be 10x. So why is that the wrong number of entries? We write 1 entry for this, then we should write 14 additional entries, so that'll be 15, and then this one would be writing the 16th entry. Oh, that's my bad. It is actually entry 17 because we are 0 index. I thought I knew computers, you know? But the issue is we're at entry 16, but counting from 0, so that's 17 total entries. So at index 16. Okay. Dare we just try it without debug? get the issue? On command 2. Okay. Attach to 661. Oops, didn't mean to exit GDB. And let's throw that breakpoint back on there. Okay. All right. So that should be the last one. And then, so let's do, let's look at our memory addresses. 1ZG of, what is it? 1ZG of racks times 8 plus 602A0. 6020A0 is that address, 602.120, and it's got whatever this is at the moment, which is, should be the same as this address, or that stack value, okay. Then plus E0, racks times 4, is the same address, okay. So we step 1. And now we do need to write the next entry as 0 because these are, we do have stuff in the high byte. So let's update our code to do that. And these are not on the 13th anymore. In fact, we really never should have been on the 13th. And we won't even try to put something in because it's not going to ask for that if we put a size of 0. Any chance it worked? Doesn't seem like it. And then we're left waiting on command 3 to edit that entry. Well, that's a good sign. We're getting further. So let's run it not debug and then attach to 2682 and continue. Okay, and I also want to do edit dream, and where do we want to, we can do it after the scanf, I suppose. So we've taken in the right entry. We're going to calculate goes to 159 to the exit. So we want to go to here, which is the success case if we enter something in. I guess we can go to this one. Plus 92. Edit dream plus 92. Okay. So we'll go through all of these. And then we're going to put 0 in that upper address. And what do we have this? Racks plus, okay. And now, why is that? What happens if we look at it this way? What? What? Oh, Lord. So my thinking was I'm going to do this. If we put in a 17th entry or a 18th entry, and then, but why did that not happen? Or why is it not aligned as we thought it was anymore? Oh. It is still aligned. It's just we need like racks -1 because we're now on the next one. Okay. So if we do NI, why didn't we write 0? Did I not do? Oh, because I killed the program. I can't step through the program that I have just killed. Turns out. Alright, I should have switched to putting a set number on this breakpoint, but such is life. Okay, so if we look at the value here at the moment and double check that it's the same, then we NI, we can look at these both. We have set the low D word. We'll hit continue and then just double check at this point with the -1 and low D word is set. So if we do NI, the high D word is set. And yeah, okay. So we hit continue. And all right. We cannot decode that. And we don't want to do these. That's going to break stuff. Because we need to do the receive here without getting anything after we actually provide the final bit of input. Okay. And overlap entry, yeah, that's fine. So when we provide these bytes, that should be fine. Now we are getting it at the final one. 20. Oh no, that's the one at 78. What is this one? Okay. And we're looking for, so let's oops. Let's maybe not do it through the command because maybe looking for the prompt is no longer correct. Why does that? I'm getting such weird behavior. Like if we take out this, somehow okay, we got a sig fault. I'll try to finish the Leviathan exercises today. There are only 8 with difficulty level of 1 to 10 should be doable. Cool, that sounds great. I think the best way to advance is to just keep practicing. Start with the easy stuff, or the stuff that's, you know, termed to be easy doesn't necessarily mean it's going to be easy for you, and that doesn't mean a good thing or a bad thing. I would say if it's not easy for you, but you're able to accomplish it, that's where you must have learned something. Much like, if you, I don't do this a lot myself, but if you maybe go to the gym or something and it's a somewhat strenuous workout experience, that's where you're getting the benefits, right? The same thing applies here. And if you have any books or sites, so I think Over the Wire is great. Hack the Box is also good, and Try Hack Me. What I have heard is that Try Hack Me is more on the introductory side, maybe, than Hack the Box. Those are going to be more, I think, similar-ish to Over the Wire. They are less focused on this sort of binary level, low-level stuff. So you're not going to find a lot of reverse engineering challenges in there. There might be a few. If you want to push your focus on reverse engineering stuff, then I think there's a site, crackmes.one. I'll go ahead and link that in the chat for you. And this is just a site with a ton of little Crack Me challenges that they range from easy to presumably very difficult. And so a Crack Me is a little program to reverse engineer in order to get it to pass whatever check. So it's similar to cracking a piece of software where you have to have a license key, but if you can reverse engineer the algorithm for checking the license, you can generate a license key that works, or maybe you can modify the binary to skip the check. Although I think the idea with most of them is to not modify the binary, but to be able to reverse engineer it to understand what it's doing. Depends on how you want to go about it, because obviously if you're talking about if you were cracking software to avoid a license check, if there's a simple way to modify the binary to skip that check, then that's still a valid, for the purposes of avoiding the license check, that's still a valid way to do it, even if it didn't require as much reverse engineering as the full, understanding how the license key is validated and stuff. So what you might find is there are some challenges that are written in a way that prevents you from doing a simple modification to the binary to skip that. Okay, why are we getting timeout there? It's not waiting on anything, is it? Oops. Okay, we're getting a seg fault. Well, I'm going to do it in debug mode. Cool. Have a good day. Thanks for joining, and good luck with working on the code stuff. And yeah, come by and update me on how that's going. And maybe in a situation like on a weekend stream when I have a little more time, if there's something you're stuck with, we could try to talk about that as well. Okay. Let's see if I've got 15 minutes left, absolute maximum. Oh, I do need it to... I don't want to quit out of this. I want to quit out of this. So I think the issue was I wasn't doing the receive input here. I took those out because it didn't work for this case. But really, we want... Let's do it that way. And then just when in doubt, add more levels of nesting of parameters. Okay, and then so we'll receive on all of those, but this one will be false for receive. We'll see what that looks like. Where do we get stuck? On command 3? Interesting. Receiving until the /n. Well, okay, let's do it debug style. 82. Okay, and we can double check that okay, so now we have overwritten that address. We're going to go to the edit command. So now we're at edit. So we can look at RAX times 8 plus that address. So that is the address that we are going to use. We put in the right index. So Rax has our, what should be the address of the GOT entry. And then, but is this not the address of printf? Oh, of course, there's tons of printf functions. And it doesn't tell me the addresses of them. Okay, well, you know, thrilled about that, honestly. So, like, maybe this is a valid address. Doesn't seem like it would be. 7FE1 ECC. 7FE1 EC. It's going to be, well, it's in the, like, executable part of libc. So, all right, let's assume that we got that calculated properly and that's not the issue. Then what are we going to do? We have EAX has the size, which is also that value. It's unfortunate, but that is the situation we're in. Is that? Think that's fine. That should be the size. Yeah. Okay. I mean, it's possible that what we need to do is go even further and do some overlaps where we can set the size associated with that index to be different, but I don't think there's really much of a problem going this route. I don't know. We'll find out. So we're gonna call read with RDX is that address. RAX is also that address. or RSI rather. So we'll read from standard in and to that address, that length potentially. Is it okay? Okay. So the issue is, I think it's waiting to read that much data. So we've overwritten the size for this. We've overwritten the pointer for this entry, 17th entry, but the size that's associated with it is also the is also the size. Like, we really need the size associated with that entry to be 8, so that when we read in the new value of data, we can provide 8 bytes. So unless we can say send an EOF, but I feel like if we send an EOF explicitly, that might close the pipe. So what I'm thinking about right now, and why did that open in its own window? No. Control G. I don't remember how to. So the scenario that I'm thinking about is like, let's say we write a new entry, and we say 1,000 bytes for that entry, but we just put in the word test. It doesn't still wait for the remaining 996 bytes, because the way the terminal works, when I hit that enter, it's actually not even sending the enter. It's not sending the new line character. It is telling the program, like, it's somehow indicating to read that it has finished sending input. So I need a way to tell it the same kind of thing with Pwn tools, basically. And I don't know if I can do that. Is there a way to... What do we have for EOF? Could say 04. Maybe that's good enough. Let's try sending a 04. Why doesn't it? Oh, because I'm not deleting that. And it's going to be on this one. Let's do it that way. Still waiting for that. Okay, so I think rather than figure out how to make Pwn tools do what we want to figure out if we can get an overlap situation where we can write the values for an address, but also have a size for that which are stored separately. Is that possible? It might not be possible. I might be misunderstanding, and I think I'm basically out of time, but if we do further entries, then okay, let's say we go a little bit further and we have written to I don't think we need to go that far. Okay. If we do it this way, then we have written to the 18th entry, but the length associated with the 18th entry will be what we put here, so it doesn't overlap. So let's do it that way. So overlap entry is actually going to be 17, but we want to do 1 minus and we want to say command 1 and the size for this is just 8, and we can just say I don't know. What is it? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Doesn't really matter what content we put in there. But if we put 8 for the 17th entry, so index 16, then the 18th entry is where we do the overwrite. When we access so 17 is where we do this one, and then we need to write 2 more, and that'll overwrite the 17th entry. Okay. I think that is fine. And now we didn't receive, we got an EOF before 8 bytes. Interesting. We got nothing. So it's seg faulted. Okay, I unfortunately really have to go right now, so I've not been paying close enough attention to the time. Thank you to everybody that's been watching the stream, interacting with me in chat. I hope you're enjoying this. I'll be back tomorrow to finish this one up. I think I'm real close at this point. Maybe another, I don't know, 15 minutes, 30 minutes I mean, it feels close, but that's also sometimes a trick. Linux how to, how's it going? Unfortunately, I'm about to end the stream. I don't know if you just got here, but thanks for joining. And see y'all later.